Hello, my name is Mwachai Simatori, and today I'll be presenting my project, which is composing from scratch a foundational implementation of a hybrid gated recurrent unit attention model for symbolic music generation. All right, problem statement. The core challenge in algorithmic music is generating pieces that are not just locally coherent, but also have a global structure. What I mean by locally coherent, this means notes and chords sound good moment to moment. Models like recurrent neural networks are excellent for sequential data like music, but they often struggle with long-term memory. This means they can forget the initial key or theme of a piece, causing the music to wander and feel disjointed. So, a key goal of this project was to tackle this problem from first principles. I built the entire generative model from scratch, using only fundamental libraries like NumPy, without high-level frameworks like TensorFlow or PyTorch. And my research question was, to what extent can a from-scratch hybrid GRU attention model generate coherent polyphonic piano music? My proposed solution is a novel hybrid architecture I call attention first. As you can see in this diagram, instead of just feeding data directly into the gated recurring unit layers, I first pass it through a self-attention mechanism. Now, how do I pass it through the self-attention mechanism? So information is passed through the embeddings and positional encoding layer. This is where the model creates a large matrix and then starts to add position to the tokens before sending all of that information through to the self-attention layer. And this is where the layer will use that positional encoding of the token and the embeddings layer, and it will create context vectors. And the context vectors are then sent to the stacked gated recurring unit, which is two layers, and the gated recurring unit will learn global structures, temporal patterns from these from the information it gets from the attention mechanism, and it will send that information through to the multi-layer perceptron, where the multi-layer perceptron will then decide on whether it will choose note on event, note off event, or hold a sustain, or essentially pause. So why this design? The self-attention layer, so the self-attention layer acts as a preprocessor. It analyzes the entire musical phrase at once, identifying the most important relationships between all the notes. It then creates context-aware vectors for each note. This simplifies the gated recurring unit's job. It no longer has the full burden of long-term memory and can focus on learning the temporal flow of this richer pre-processed information. This approach is directly inspired by the principles that make large transformer models so successful. Now let's look at the pipeline, which is the process of getting from raw MIDI files to training examples. So the model is trained on a single continuous stream of integer tokens derived from the POP909 dataset. So step one, parsing and merging. So the Python MIDO library is used to read individual MIDI files from the POP909 dataset. All parallel tracks, which like melody, piano, etc., are merged into a single chronological stream of musical events. And then step two is the event-based tokenization. So each musical event is converted into a unique integer token. This process is called event-based tokenization, which I just stated. And my model uses a vocabulary of 420 unique tokens, which captures the full musical performance, which is note on, note off events for all 128, which is 128 tokens, 128 bins for time shifts to capture rhythm, 32 bins for velocity to capture dynamics, and tokens for the sustain, pedal, and start end markers. Finally, creating training examples, I use a sliding window that moves across this long stream of tokens. And so it's 50 tokens. That's the sequence. So the input model X is a sequence of 50 tokens, and the target, the model must learn to predict Y, which is Y. And this is the very last token, which is the 51st token. Now the results. These graphs show the model's loss and accuracy during training. So on the left, you can see the validation loss shows a clear downward trend, which confirms the model was successfully learning and generalizing from the data. On the right, the validation accuracy reached a peak of about 37% for a 420-way classification task where random chance would be less than 0.25%. This is a very strong result. However, you can also see that after a few epochs, the validation loss began to fluctuate and rise while training loss kept decreasing. This is a classic sign of overfitting, a primary challenge when building models from scratch. To combat this, I used an early stopping mechanism which saves the model at the point of the lowest validation loss, ensuring I use the version that generalizes best. But objective metrics don't tell the whole story. The ultimate test is how the music sounds to a human. I conducted a listening study with 10 participants. The feedback was consistent. The model's main strength was local coherence. Participants were surprised it could generate harmonically plausible chords like major sevenths and maintain a steady rhythm. However, its main weakness was global structure. The most common complaints were long unmusical pauses and chords that, while correct on their own, they were misplaced in the larger progression. The model failed to develop any memorable theme. And overall, the generated music received an average rating of 4 out of 10, acknowledging its technical ability to form chords, but recognizing its failure to create a cohesive piece. Now let's listen to a short piece composed by the trained model. Hi again. All right. So for the data preparation, I use the this is I use MIDI parser. So I created a MIDI parser for data preparation. Just like in the slides, there are certain tokens for note on, note off, time shift offset, velocity sustain on and off, and end tokens. And these are used to translate the MIDI events that are in the MIDI files into tokens that my model can train on. Firstly, I start off by scanning my dataset for MIDI files, and I add that into an array, which is called MIDI files. And then from there, I start with the parse and tokenize. And over here, I take a maximum number of files, which is just 20 files, which is what I train my model on. And then from there, I start to use the Mido library to essentially firstly merge all tracks into one single chronological stream. And then from there, I start to from there, I also start to look for all the time events, all the time shift events, and I add that into the single stream tokens um, array. And then from there, I start to translate the note on, note off, and control change um, events into tokens, especially the velocity tokens as well. And then from there, I start to save that into the tokenized data.pickle. And that is how I created my my tokenized data set for my model. Moving on to the model. So I'll be talking more so. So firstly, I initialized my weight using the Xavier initialization scheme. And I also initialize my atom optimizer variables within the initialization function. Moving on to the forward method. So firstly, I calculate the alignment scores. So I do this using a small feed forward network defined by the weights WA and W and VA. So the input sequence is passed through this network, and this produces a raw score for each token. And a high score means the model thinks that that token is very relevant to the current prediction. After that, I apply the softmax onto these scores to get my attention weights. So I do this because it forces all the scores to sum up to one. And you can think of these weights as percentages of how much attention the model should pay to each input token. And then from there I compute a matrix multiplication between the attention weight and the input from the embeddings weight to get the context vector, and then I return that context vector. And the backward method, during training, this method just uses chain rule to calculate the gradients for the attention weights, WA and VA. And this allows the model to adjust over time, getting better and better at identifying which parts of the musical phrase are the most important for making coherent predictions. As with all my layers going forward, I also built the atom optimizer logic directly into the layer, which you can see right over here. And this makes my design cleaner and more modular. I'm going to start moving on to the gated recurring unit. So two activation functions, which is sigmoid and hyperbolic tan. And these are for my gate calculations, which is the reset gate, the update gate, and the update of the hidden state as well. And they are also derivative versions of it, and these are used for the backpropagation. I also used a version of the Xavier initialization scheme over here, and I also what do you call this, initialize my optimizer variables. Moving on to the forward pass. So firstly, for the forward pass, I'm just going to explain the reset gate and the update gate. So first, the reset gate decides how much of the so the reset gate, sorry, the reset gate decides how much of the past information is irrelevant and should be forgotten. And you can think of it as a gatekeeper that looks at the new node and the old memory and says, okay, based on the new node, we can forget about these specific parts of the old memory. Then the update gate decides how much of the old memory should be carried over to the new one, and it essentially determines the balance between keeping the old information and updating it with new information from the current node. And as you can note over here, we are doing this on a time step by step we're doing it step by step within time through time. So we're updating these gates through time through the sequences that we get as well. And then from there, from there, I calculate the candidate new hidden state. And then the final hidden state will be updated using the reset and update gate. Okay, moving on to the backward pass. The backward pass is just a implementation of the backpropagation through time. It's a complex process, but the core idea is that the error gradient flows backward, not just through the layers, but also backward through every single time step of the sequence. And this is how the model learns the temporal patterns in the data and figures out how to adjust the gate weights to make better predictions. And again, just like my other layers, I've also encapsulated the atom optimizer logic right here to keep the component self-contained. All right, now I'm going to move on to the multi-layer perceptron. One thing to note as well is that I used the leaky ReLU function instead of the original ReLU function, and I chose this to avoid the dying ReLU problem. In standard ReLU, neurons can get stuck in an inactive state if they only receive negative input. And so by using leaky ReLU, I avoid the dying ReLU problem. I've also added a critical regularization technique, which is the dropout. So during training, it randomly shuts off a fraction of the neurons, and this forces the network to learn so this forces the network to learn redundant representations and prevents it from becoming too reliant on any single neuron. Also, another key implementation is the technique called inverted dropout, which you can see over here. And this is an efficiency choice, which makes it that I don't have to make any changes to the network during inference time. Firstly, also another note, I also during for the initialization, I initialize my weights using the HE initialization, which is designed for layers that use ReLU-based activations, and it prevents gradients from vanishing or exploding, leading to much more stable training. I also initialize my biases to 0, and like many other layers, I initialize my atom optimizer variables. Within the forward pass over here, I just compute the input. I just compute the matrix multiplication between the input and the weight, and I add the biases from there. Within the backward pass, I just calculate the gradients for these weights and biases using the chain rule. And just like many other layers, I also um, I also apply my atom optimizer logic within this layer. And this, like I said, for the other layers, makes it much more cleaner and much easier to manage. I'll be moving over to the overall model architecture. These are my two loss functions. I use the categorical cross entropy loss function, as I'll be dealing with a 420 way category um, model. So the model has 420 choices, 420 tokens to choose from. So I use the categorical cross entropy. This categorical cross entropy grad function is used in the backward pass, and this is just used to calculate the loss and just propagate the loss all the way through my model network. One thing to note is the positional encoding. So my attention mechanism looks at all nodes in the sequence at once. This basically means that a melody played forwards and a melody played backwards is basically the same to the attention mechanism. And to solve this, I implemented the sinusoidal positional encoding. It uses a clever combination of sine and cosine waves to generate a unique signature for each position in the sequence. And I chose it unlike other learned positions, as it can generalize to sequences longer than any it saw during training, making the model more flexible. All right. So in initialization, one thing to also note is I've also added an embedding dimension, an embedding layer. So firstly, the model cannot work with raw token numbers. So I have an embedding weights matrix, and this is a lookup table where each of my 420 tokens is mapped to a rich 128 dimensional vector, and this allows the model to learn the relationships between different musical concepts. Then from there, I initialize the stack of two Getty recurring units. And then from there, it is the three dense layers, um, which acts as the final classifier. It takes a learned musical context from the Getty recurring unit and makes the final prediction. All right, moving over to the forward method. Firstly, the input tokens are converted into their embeddings vectors, and the positional encoding is added directly to them, and this injects the crucial information about the sequence order. And then I apply the attention layer before the gated recurring units, and this attention layer just creates a context vector that summarizes the most important parts of the entire sequence. And then I add the summary vector back to every single token embeddings. um, this basically means that when the gate occurring unit is processing a node at step 5, its input contains not just the information for that node, but also global summary of the entire 50 token context. And this gives the gate occurring unit a much more powerful input to work with at every step. And then from there, I do the recurrent processing. This is where I pass this information through my two stacked gate occurring unit, which processes the music sequentially and updates their internal memory. And then from there, I do the final prediction where the whole sequence is processed and then sent through the multi-layer perceptron layers. And at the end, I use a softmax to produce the final probabilities for every possible token, and I return these probabilities over here. And the backward pass, simply I just pass the error gradient. So I pass the gradients all the way through the layers, back through all the layers in reverse. And this is what I use to update my model. And also at the end over here, though, at the end of here, I also do the what do you call this? The atom optimization onto the embeddings vector that I've created. All right, moving on to the train.py. So over here, one thing that is important over here is the load and prepare data. So over here, just imagine a sliding window moving over the tokens. So the sliding window is of size 50 tokens. And for every 50 token sequence in the data, it creates a training example where the 50 tokens are the input and the 51st token is the target that the model has to predict. A crucial detail that we have to note over here is this line over here, these two lines. This is crucial as I make sure that I filter out any window that crosses the boundary of a song by checking for the end token. All right, this over here just plots the training history. This is self-explanatory. So over here, I split my data into 90% training set and 10% validation set. Also, another thing to note is that I implemented the exponential learning rate decay. And the idea of this is that the model starts off with a relatively high learning rate to make fast progress and then gradually decreases it. This allows the model to make smaller, more precise adjustments as it gets closer to a good solution. Now, within the training loop, firstly, I randomly shuffle the training data. This is good for generalization as it ensures the model isn't learning any patterns based on the arbitrary order of the original songs. Then within the training loop, which you see over here, firstly, I get the model's predictions through the forward pass. And then from there, I um, calculate the loss over here. So compares the prediction to the correct answer to see how wrong it was. And then I perform a backward pass to backpropagate the error through the entire network, where all the models will be updated. And then right after that, I do a validation step where I just allow the model to get a prediction through the forward pass, calculate the loss. And one key note over here is that I do not call the backward method, as the model will just be making a prediction on the validation set. I also implemented a early stopping mechanism over here. So it saves the model's best weights. It saves the model's best weights if the model has seen the best validation loss so far. And if it hasn't, for a set number of epochs, the training stops automatically, and this ensures that the final save model is the one that performed the best on unseen data. Moving over to the generation process. So within the generation process, firstly, what I do, so firstly, one thing we need to talk about is the sample with temperature method. So over here, I just implemented temperature sampling. I created this so that I can allow the model to be more creative instead of just predicting the right nodes over and over again, though, as this would be boring and repetitive. So one thing to know over here is that a low temperature will make the model more conservative and predictable, and a high temperature means that the model will be more adventurous and will pick the less likely nodes. And this function reshapes the model's output probabilities based on the temperature before sampling the next token, allowing me to control the balance between coherence and creativity in the final output. With the get seed function, so over here I didn't want to do an unconditional generation process. So over here I created um, an automatic conditional generation process where the model, so firstly I use the same sliding window logic from the training process. And essentially what's happening here is that it will look for the start token. And from here, all starting phrases, 50 token phrases will be used to, will be fed into the model for the model to generate more nodes from that 50 token sequence. So from here, I just get all the starting phrases of each song or each MIDI file in the dataset, and I use that to prompt the model on what it should do from there. All right, so now moving on to the main function over here. So firstly, I load the base model, which contains the fully trained weights. And then after that, I get the seed. I call get seed function to get high quality starting phrases. And then within the generation loop, this is where the model is fed the starting seed. And this is an autoregressive process, which means that the model's output at one step becomes part of its input for the next step in the loop. So it takes the last 50, so it takes the 50 token um, seed sequence as input, and then feeds this into the model's forward pass to get the probabilities for the next token. And then the sample with temperature method is called to pick the next token. And finally, the newly chosen token is appended to the end of the sequence, and this loop repeats, generating the music one token at a time. And then from there, I generate my tokens back into a MIDI file, which you can see over here. And then after that, I save the MIDI file and I start playing the MIDI file from there. And I'll start generating the song right now.